Hey there, Lonnie. How you doing?
Good morning, Professor. I'm good. How are you?
Good, good. Welcome. Hope you are. Did you watch the video?
Yeah, I watched the first one. I was
Okay.
really interesting.
Yeah, it's pretty neat stuff. Okay, cool. Hey there, Lonnie. How you doing? Hey, who's that?
Good morning, Professor. I'm good. How are you?
Good, good. Welcome. Oh, sorry. Hope you are. I have to mute my. Never mind. I'm like, who is that? Who's that talking? That's me. All right. Well, hopefully we'll get a couple more people here. We have somebody watching on the YouTube. Not sure who they are. Who are you? Who's watching? Anyways, so yeah, we're going to talk about string theory, and it's a pretty awesome idea. And then talk a little bit about, yeah, where it's going. Actually, there was another, since there's not too many people here, maybe we could take a second to talk about something else for a moment. There's a very famous, well, a guy I know, he's a physicist, but he actually is famous for me for some of the other computational work that he's done. His name is Stephen Wolfram. Have you heard of that? Have you heard of his name?
Wolfram sounds really familiar, but
Okay. So there's a website that he's created.
yeah, that's probably what I know.
Yeah, it's called Wolfram Alpha. So it's kind of an interesting thing to look at. It's actually like, what do you want to know about, right? So, you know, how many, whatever moons away is the sun? I don't know what that means. Put random questions, but it tries to calculate things for you, interpreting moons, right, as a unit. Okay, good. And then, okay, so it didn't quite figure that out. Okay, so it was a little confused by my question. How many McDonald's are there? I don't know, just random questions. But the weird thing is it can answer a lot of questions. You see, it's kind of trying to interpret my natural language. Oh, look at this. Oh my gosh. Oh, that's too funny. This is actually very interesting. Okay. What is string theory all about? Let's see what it's asking. Oh, I didn't spell it right. String theory. Ooh, music work. Okay, never mind. Oh, particle physics topic. Okay. So anyways, it's kind of an interesting thing to play around with. Oh, didn't work very well. Okay. So let's see. What is the number of seconds in a year? Okay, so you can ask questions like that. Okay, so convert. See, so this is actually the calculation or the instruction that I gave it, right? I didn't tell it to do that, but my natural language gave it that understanding to convert a year into seconds. And there's my number. Okay, cool. So, and then here's some, oh, this is funny, right? The what? 0.9993, the orbital period of a year of the Earth. Funny. Comparisons of half-life. Okay. Anyways, it's kind of a funny little website. But why am I bringing that up? Hey, we got a bunch of new people. All right. Say good morning, everybody. So everybody say good morning. Good morning. Okay. So yeah, so this guy has come up, Wolfram, actually, Stephen Wolfram has come up in another way, which is kind of funny. And I wanted to just bring that up with you guys. This is, why is, I pinned your video. There we go. Hey, good morning, everybody. So he just came out with an idea that I think is kind of intriguing, and I haven't read it super carefully. I've only just kind of given it a cursory glance. But Stephen Wolfram claims to have had an epiphany about reality, and he is actually, it's kind of like string theory. So that's the reason why I'm thinking it would be interesting for you guys to think about. But Wolfram has an idea about what reality is. So let me just see if I can find a quick little space. Where did I read the article? Theory of Everything. You could search with me if you want. Maybe you can find a better. Okay, well, Science News, Scientific American, no. Okay, oh, here we go. Steve, okay. Well, this is actually his, oh yeah, Wired. It must have been Wired. Okay, so this is an interesting idea, right? So here's somebody, this is a big claim, by the way. So one of the ideas in science is if somebody makes a really big claim, you should be incredibly critical. You must be incredibly critical. The more incredible the claim, the more incredulous you should be. It must have a lot of evidence to support it. So here's the guy, Stephen Wolfram, and he is a pretty intelligent fellow. So I'm not saying that I actually think his ideas are interesting and definitely worthy of your time and consideration. So yeah, so anyways, a novel, I'll read the first paragraph, right? We'll just get an introduction. The novel coronavirus has derailed everyday existence for all of us, forcing us to make difficult choices. But a few weeks ago, Stephen Wolfram's dilemma was unique. What should you do, he wondered, if, right in the middle of a pandemic, you were ready to announce that you had made historical progress, at least as you saw it, towards solving a fundamental physics question. If you felt you had figured out the path to the holy grail of physics, a unified theory making it possible for the first time to discover the underlying rule of our entire universe, one that intertwines relativity, gravity, and quantum mechanics with an elegant coherence, great word. But what if you were ready to ready to release the tools and background materials that would enable a crowdsourced effort to take physicists over the finish line? Okay, so this is supposed to be a teaser. Wired is pretty good at this. Articles are kind of interesting. I like Wired a lot. Lots of ads though. Okay, so this is a visualization of what he's trying to do. And there's a combination of ideas here, but let's go down to the very beginning. Okay, here's some more pictures. What is he trying to do? He's trying to start, I actually feel like, never mind, I should just jump to his page. There's a link here somewhere where he tries to state very, very succinctly what his key idea is. It's 100 pages long, by the way. This is not the right place. Okay, hold on, let's try something else. Let's try another one. Let's try this one. Okay, so that picture is meant to show you something complex. That's actually an interesting, complex situation, you know, kind of, what the heck is it? I don't know, it looks almost like a brain or something, you know, an outline of a brain. Hypergraph, okay, so I don't need to see you. Okay, here we go, continue, all right. Summary document, okay, so maybe this is the one that I should go to. Yes, I think that's it. In a summary document, released April 14th. Okay, so this is it. Okay, this is it, all right. Blah, 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 blah. Actually, you know what? I started reading this. So actually, he has a link to something quick. I've been working for 50 years. Blah, 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 blah. Okay, never mind. Okay, where is it? Here it is. Okay, so start off. Here it is. This is the basic idea. Okay, so I've written a 448-page technical exposition. Another member has 260. Okay, so we're not going to read this in 2 seconds. There's a project website. Okay, but anyways, okay. It all begins with something very simple and very structureless. Okay, this is the key part. We can think of it as a collection of abstract relations between abstract elements, or we can think of it as a hypergraph, or in simple cases, a graph. We might have a collection of relations, like one is related to two, whatever it is, right? You see, these things are very general. 2 is related to 3, 3 is related to 4, and 2 is also related to 4, okay? So this is a relationship picture, and they can represent anything, right? These could be people, these could be ideas, right? It's a very generic, simple kind of graph. But you see the arrows indicate the functionality, right? Somehow there's I don't know why they're not bi-directional. Anyways, we'll get back to that. I don't know why. And what he does is he says that you take this simple thing and you complex it. Okay, so then what you do is you find a way to transform it, right? In a very simple, with a few rules, a very, very simple set of rules. So here's one rule. It says that if you have two things that are related to each other, X is related to Y and X is related to Z, here's a transformation that you can make, okay? And then do that transformation. So what he says is that, you know, you start off with something simple, and when you apply this rule, you get something a little more complicated, and you just keep doing that. And before long, you get things that are incredibly complicated. So his idea is that maybe the universe looks so complicated to us because it's had a long time to develop. But really, the number of rules that underlies the structure of everything could be very few. Could be just a few rules that explain everything. Now, keep in mind that even if he says this is what's going on, he still hasn't proven that it's worth anything. So what, right? So what? But the point in science is that if you discover that there are only a few rules to explain everything, then you can actually describe how things might evolve. And so it might allow him to make predictions on what how it will continue to evolve, which I think would be kind of interesting. All right. So anyways, that's an interesting side topic. I don't know if you're interested in that, but somebody's chatting. Somebody says, oh, good. Yeah, that's actually all right. So that's the link that I ended up going to. So I don't know if it's valuable or not, but it's kind of an interesting idea that maybe with a few set of rules, a few simple rules, you can explain everything. That would be kind of cool. Does anybody see the connection between what he's doing and string theory? You could write a comment in the YouTube channel, or you can write a chat comment, or you can say something out loud. One of those would be good. How does this idea connect to string theory? The problem with remote learning like this is it feels like I'm all by myself. Hello. Oh, yay. People are talking. Leonie, yes.
Yeah, I think string theory also tries to explain everything by simple theory. So like that everything is built out of energy strings, kind of.
Okay, so that's actually the fundamental unit is something that's kind of simple, right? It's just a little tiny, I mean, I don't know what it is. Do you know what it is yet?
No.
What is this? It's energy. It's some little tiny thing. It wiggles. I don't, a string, right? They're really imperceptibly strong. Yes, I agree with you. I think that that's kind of the idea that it's not the strings that are complicated. What they can form ultimately is something incredibly complicated, but they themselves are simple, right? So yeah, I agree. I think that that's, in a way, he's kind of created this new idea, but really this new idea is already something that we've seen in string theory. So okay, all right. Well, so string theory is what you guys are starting to learn about in the elegant universe. Was anybody anything that you learned in the first episode that you found really interesting that you want to share, that you remark on as kind of like, wow, that's crazy? Anything you read about or learned about that is new to you, for example?
It's not exactly new, but
okay.
while watching the video, when we had all of the side commentary from multiple different scientists, one of them was pointing out one of the biggest problems of general relativity, comparing it to quantum mechanics. And for a while, like everyone says, yeah, you use general relativity for big and quantum mechanics for small, but
Mm-hmm.
it's all supposed to apply everywhere. And he just had the perfect little way of saying, well, general relativity applies everywhere and quantum mechanics applies everywhere, but there can't be two everywheres. And as soon as he said that, it all clicked in my head. And I was like, oh yeah, there really can't be. So
Right.
what's going on with quantum mechanics in the big scale and general relativity in the small scale?
Okay. Yeah. Well, this is a really big question, right? Because things don't work, right? We get infinities. We get things that, physicists look at and say, that's crazy. That can't be right. And I mean, we think that's true, but I don't know. I don't know that. Maybe the universe is crazy, and what we're seeing is that craziness. Or it really, it's more likely that when we get things like infinity and it just doesn't make any sense. It's probably that it's garbage. Okay, or not garbage exactly. I shouldn't say garbage. In fact, I learned something just a couple months ago when I went to a conference about string theory that I found really remarkable. I think I told you guys. Did I tell you? Do you remember what I told you about that? I don't know. I went to the teachers conference, and one of the things that they said is that string theory has produced something remarkably similar to Einstein's field equation of general relativity. Remarkably similar, right? And you're like, wow, that's awesome. And then they told me the tiny little detail that is actually, unfortunately, the real problem, except in their version of it, the cosmological constant is negative and the universe cannot be expanding. Okay, so that's a mild little problem. Anyway, yeah, so the best, closest theory to general relativity that has been created by string theory has the wrong sign for the cosmological constant. So yeah, well, okay, what do you do? It's not good, it doesn't work. Anybody else? Brandon, what did you see in that first episode that you want to share with us? What was remarkable?
I never got around to watching it.
Oh man, dude, that was your homework. Okay. Well, so you have 3 episodes to watch for next Monday. And you got to take the quiz. Okay. But really I think you're going to find it really enjoyable. They're not that long either. And the guy is really fun to watch. Brian Greene is a really great speaker. I mean, he's a little over the top sometimes too. He's good at public speaking. He's really great, actually. How about Leona? Leona, anything you saw that you want to remark, or can you share something with us?
Yeah, I just think, well, for most of the video, it was a pretty good overview of what we've been learning the whole semester.
Okay, so you saw a lot of connections.
Yeah, so having it condensed in kind of a crash course type way,
Mhm.
it made me see a lot more connections and see how like everything fits into place and leads into string theory. Because
Okay.
when I'm like reading through the book, it's not always easy to see all those connections and to see how they
Okay.
all fit together.
How do they fit together, right? So does this episode talk about Einstein though?
Yeah.
Okay, so you guys, anybody have, actually, can you guys talk a little bit about Einstein? Is there anything about Einstein that you learned in this episode that you didn't know about before, or maybe you knew? What did they talk about with Einstein? I don't remember. It's been a while.
One of the things that Brian Greene mentioned about Einstein was that right when quantum mechanics was starting to make its debut, rather than even find any interest or bother learning about any of it, he decided to shut himself away and really focus in on his general relativity.
Right.
Which he probably shouldn't have done.
Well, it was his choice, and he was getting older, and unfortunately, it seems to be a human trait that we get less flexible, both physically and mentally, as we age. I don't know if that has to be true, but it definitely, see, Einstein, it's hard to understand how crazy his life was, right? He was so incredibly productive in the early part of his life. The discoveries that he made were just revolutionary. And then, you know, everybody looked at him as some kind of wonderkind who, you know, it's just, he's impossibly brilliant. And he really worked very hard to get the work done that he did. You know, he was very prolific for quite a while. But as he aged, he kind of drifted away from science and went into more philosophy. And he's actually written quite a bit about philosophy, and I don't really assign reading for that, but I have a book on my shelf that he wrote, and he really became a humanitarian and wanted to, you know, to work on problems of the human kind of psyche and the human motivation and the human elements, you know, that are not scientific. Well, they're not as scientific, sorry, they're much more ephemeral. They don't have concrete values that you can put down on paper. But yes, that was a huge thing, right? What was the phrase that you guys probably learned about from Einstein and quantum mechanics? He had a phrase that he used. He didn't like quantum mechanics. One of the things he said.
He said God doesn't play dice. That's not the exact phrase, but
Yeah, something like that, right? God cannot play dice. What does he mean by that? What is dice? What does that even mean?
because like quantum mechanics is all about probability and uncertainty, and he thought that that wasn't the way that it really is.
So this is a huge thing, right? Actually, philosophically, I'm not a fan of you know, a philosophy that says determinism, right? It's called determinism. So that events unfold in a way that is calculatable, right? That is determinism. It says that if you know perfectly the conditions, the starting conditions of a problem, then using the laws of physics, you can calculate the next state and the next state and the next state. You can calculate the future. Everything is determined. And in fact, that set of initial conditions is what determines every future state. And you could apply this to human, right? I mean, really, it kind of says that everything in our lives is calculatable. If you have that idea that the universe is just a big machine and it's functioning to do the calculations, it's actually calculating. We are calculations of a kind, right, in the computer of the universe. And we are, you know, there's a number that we come up with at the end of our lives, right? Well, that's bullshit, excuse me. I just can't be right. It's just not right. There are moments in our life when we make decisions that completely change the path that we were on, right? I mean, we do this, it just happens. I mean, maybe it doesn't happen too often to you yet, but I promise that in your life, you will need to make decisions. And one way you could end up this way, and another, I mean, there's really dramatic changes that can happen in your life, and you have to be responsible for making those choices. I believe in free will, but that free will gives us the possibilities that quantum mechanics kind of shows, right? That nothing is deterministic. Although, how do you get that, right? How is it possible that all of these scenarios are available to us, right? Why is it? Is the universe really that big? All right, so anyways, philosophically, there's some really fun things. So Einstein hated that idea. He believed that quantum mechanics, because of its probabilistic nature, was just wrong. He couldn't agree with it. That things, he loved the surface topology of general relativity, and it gave him a sense of security, right? It was something, even though it's very ephemeral, you can't see it, it is still very strong and stable, and gravity, and you know, it gives us a really tangible result that we can live with. But quantum mechanics, you never know what's going to happen, right? You can only say with probability something is about to occur. So all right, so I need to lecture on something, and I'm struggling to find some ideas, but I do want to talk about this beautiful idea of string theory is just how simple it is, right? It has strings. The strings are very small. And one of the things that you should be aware of is that the strings are so small that we cannot perceive them, right? They are not detectable by any instrumentation that we currently have. And it may not ever be detectable, although I hate to say ever. In fact, I'm really, honestly, I just don't believe that we have limitations that we are aware of. So what seems impossible now in 100 or 1,000 years might be commonplace, right? I just don't believe in placing those limitations. As long as we don't destroy each other, we have the capability of evolving into very advanced beings, right? And we are actually, anyway, so that's another topic. Never mind, I don't want to talk about that. Let me talk about strings then. And I actually, a couple years ago, when it was kind of fashionable, I was learning how to do Flash, and kind of fun. And I made something I kind of actually, I'm still pretty proud of. It's a little Flash animation, and it's a little tiny string, right? Well, it's not tiny, it's meant to be a big string. But let me go ahead and flip down to the paper, and you guys should take some notes on this because I'll find a way to ask you questions on it. But it turns out that if you have a string, let's make a little string, and it has a length L. And actually, I'm going to do something that you should be aware is not always true. But I'm going to go ahead and I'm going to take my little string for the sake of today's lecture, and I'm going to tie it between two fixed points. So it's like a guitar string or any stringed instrument actually. And may or may not be the strings that we're talking about in string theory. But I want to talk about strings because they have an interesting feature, and these features are found in string theory. And so I want to make this vibrate, a vibrating string. Okay, so this is a little bit of physics, but I think it's such a fun part that you'll enjoy this. But it turns out that strings can vibrate in a variety of ways, and yet there's some important considerations. No matter what this string does, however it vibrates, it can oscillate up and down, right? The only way that it can move, well, actually, I shouldn't say that the only way that it can move, but the most important mode of the string is a vertical mode, right? Where it moves up and down. The displacement so what is a wave? A wave is a disturbance in a medium or not, right? Actually, it's really not necessarily true. Disturbance in a medium, but actually, when you talk about light, it's a self-propagating wave. That's another little tangent. Gravitational wave. Does a gravitational wave have a medium? And the answer is actually it does. It's space-time, right? So it makes space-time start wiggling. But anyways, okay, this is a regular string. Let's not get off on a tangent. Okay, vibrating string. It turns out strings can vibrate in a whole variety of ways. In fact, let me go ahead, and this is the original, this is the equilibrium state. Okay, when it's just straight like that. And then what I have to do is disturb it. So if it was a guitar, you could pluck it, right? You can move it, you can disturb it. And you can pluck it anywhere you want, right? Actually, you can pluck it or hit it. You can do all kinds of things. And actually, it turns out that at any moment, I might get something kind of crazy like this. A whole variety of, actually, you never get a point like that. That was the wrong thing to do. You don't get a point. But if I looked very carefully at a vibrating string, I might see something kind of crazy like that. It's just chaos. But what you find is if you watch for just a few moments, that the string will fall into a state which is much prettier than that. And so what we tend to see is a string that you pluck, right? And I'll put a dotted line to show the equilibrium state. Very quickly kind of falls into or relaxes into a state which is known as the first harmonic. Okay, and so I'm going to draw that for you, right? I'm going to draw this first harmonic. Oops, that didn't work. Sorry. Supposed to be fixed here. Okay, I got to look at the paper. Sorry. This is so weird. I'm looking at the screen when I'm drawing, and I shouldn't. I should just look at the paper. All right. Anyways, we will do that later. Okay. So this is called the first harmonic. So what is a harmonic? This is kind of an interesting. So what's going on is that the string is actually vibrating up and down in the middle like this. And just to again, if you've had physics, you've probably seen all of this before. But if you've never taken it, I still require you to know a little tiny bit right here. We have some boundary conditions. So the word boundary conditions is a generic idea in physics. And we've talked about it before, the boundary conditions for the universe, for example, right? The initial conditions, the boundary conditions could be the initial conditions or something related to the physical space. And in this particular situation where I have a little piece of material tied between 2 points, this point cannot move and this point cannot move, right? Those are special. It's the place where the string is tied down. They cannot move, right? And they have a name, okay? So you want to know this name. These are called nodes, right? What is a node? A point that does not move on a string, whatever, on a, that is period. Because you know what? This could be applied to multiple dimensions. By the way, this is a one-dimensional object. Let me go back to that concept, right? So these harmonics that I'm going to show you are generic, but we're going to do the one-dimensional case first, and then we'll talk maybe about more advanced versions of that. So these are called the nodes because they can't move. And then in the middle, we have an antinode. And the antinode is where all the motion takes place. This is the place that moves, right? This is the place that moves. So what does this look like? It looks kind of like a jump rope, maybe, but and sometimes it could be. But it's basically vibrating up and down. And this has a particular wavelength and a particular frequency. And so the first harmonic has a wavelength associated with it. I'll put a 1 down here. And a frequency associated with it. And now I'm not going to do a lot of math, okay? It's just meant to give you a little sense of how this works. So what you can't see in here is that there's actually a wave. And the wave is bouncing or reflecting back and forth on this tiny little piece of string. And you're like, well, how does that show me the wave? Well, it turns out, remember, when the wave bounces back and forth, it actually meets itself in the string. And there's 2 ways that we talk about waves meeting themselves, right? Sometimes when a wave meets another wave, and this time it's meeting itself, it creates a larger wave. That's the antinode, because it's constructive interference. And then sometimes you get the wave canceling out. You get destructive interference. Okay, so actually, why don't we write that down? What is a node? It is destructive interference. And what is an antinode? It is constructive interference. Okay, so I was struggling to show this to my students and they weren't getting it. So I made this little application, and I am happy to share it with you today. So this is a little flash animation that I created. And let's see if this will work now. And can you see the flash? Can you see something? Can you help me out and let me know? Okay. So there's down here harmonic number 1. And then there's this thing called the phase shift. And I put in here to help you understand, this is really time that we're talking about. So there is a blue wave, which I can't see right now. And there's a green wave, which I can see. And that's because I drew the green wave after the blue wave. But anyways, let me go ahead and start time flowing, right? Now you can see it, right? So the blue wave is traveling towards the right. And the green wave is traveling towards the left. And what you get when you put them together is the red wave, right? The red is what you see the string doing, right? You can't see the green and the blue. You can't see them. You just see the outcome of both of their action on the string. So a couple little tiny details to show. When you tie a string down, there's a kind of a funny thing that happens. And I actually could show you with another app. But when the blue wave hits when it reflects off of this fixed point, something funny happens. It flips over, and it has to flip over. And the reason is because it's tied down there. It can't move. And so when you pull with the string on this point, it pulls back on you, and it doesn't go anywhere. So you have to go down, and it ends up flipping it over. It changes the phase by 180 degrees. Again, if this were a physics class, I would require you to know that. You don't have to know that. And then the same thing over here. So what happens when you add a positive thing and a negative thing together? What do you always get? 0, right? So what kind of interference is it? Positive plus negative, you get destructive interference right here at both ends. But if you watch in the middle, look what happens, right? You see how you get different versions, but in fact, you're always getting constructive interference there. And it's just depending on what part of the wave is being added together that you get a high point or a low point. So you can watch this thing, just watch the red now, just watch the red, right? The red oscillates up and down, and that's one full cycle of the wave. Okay, so what does the second harmonic look like? And by the way, this is what a guitar string sounds like most of the time when you play it and you wait for just a moment. That's the sound that comes out. It's the sound that's made by this particular, actually, you know what? Let me do one more little note for you. Okay, little note, you see what I did there? Okay, just kidding. Okay, so if I draw a picture of the wave, what part of the wave am I seeing at any moment, right? And so if I have this little arc right here, you can see that it goes from 0 to a positive value to 0 again. Is that a full wave? Is that a full wave?
It's only half a wave because you go
exactly. It's exactly 1/2 of a wave. 1/2 of a wave. So if 1/2 of the wave is equal to the length L, then what is the wavelength? It must be 2L, right? And it turns out, again, if we're not going to do all the calculations, but the speed of a wave is equal to the frequency of the wave times the wavelength of the wave. And assuming you don't change the tension in the string, the speed will be constant. And you can calculate the frequency is going to be the speed divided by the wavelength. So this is a little bit of physics on harmonics, okay? It's not a big deal. But the first harmonic is the one that you get from the first wavelength. The frequency is based on the first wavelength. So what does the second harmonic look like? Okay, I'm just going to ask you to do a couple just because then you can kind of get an idea. And in the back of your mind, you want to think about it. What are the strings doing? Well, this is one of the ideas. They have harmonic frequencies, okay? So in the second harmonic, something funny happens. There is a third node in the middle of the string. And so if I watch this, the red line will be something that looks like this. And the red line will vibrate up and down. So I'm going to draw the other version. And these are going to vibrate up and down. So what are the three fixed points called? They're called the nodes, right? And what are the places that are vibrating up and down called? The antinodes. Okay, so again, we're not taking physics. This is more than I need to know, right? Well, it's just kind of a fun thing. If you notice back in the first problem, the first harmonic had a single antinode, right? A single place that vibrated up and down. And how about this, the second harmonic, right? The second harmonic has two of these antinodes. Okay, so actually, again, what do you notice, right? The length of the string. Now, if you follow this path, how much of the wave can you see fitting in the string? So this time, how much of the wave do you see? You see the entire wave, right? The whole wave, one full cycle of the wave is equal to the length L, right? So what just happened to the wavelength, right? Did it get longer or shorter? Well, it's just half as long as it was before, right? So the higher the harmonic, the shorter the frequency will be. In fact, because the number of half waves fits, the greater the number of half waves that you can fit, the shorter the wavelength must be. And what about the frequency? Well, the frequency this time is going to be, now it's going to be V divided by L. What just happened to be, let me put it up here, V divided by 2L. What just happened to the frequency? If you look, it's missing the 2 that's here, right? And so just to finish this off, it's 2 times the first harmonic frequency. So this is kind of a cool little trick here, you know, that what happens to the harmonics is the higher the harmonic, the higher the frequency will be. And so we actually are believe that our strings in string theory have this ability. So if I jump to the second harmonic, now I see this wave, and I reset it, but anyways, okay. So I see the blue and the green, and again, watch the red line, and it does this oscillation. But all it is the waves bouncing back and forth within the string, within the medium. And it's funny, when I first made this app, I had it go up to anything you wanted. And so I would put it up to 200 and my computer wouldn't even move because it was calculating all of these things. It was pretty cool. Anyways, you just get more and more of these antinodes, okay? So the higher harmonic, so you should be able to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 antinodes for the 10th harmonic. And it looks really complicated, but it's really not. It's just the same thing that we've been talking about. But of course, the higher the harmonic, the higher the frequency of the harmonic will be, okay? So I think this is kind of a neat idea to understand, because strings are going to be having harmonic frequencies. So there's another, again, I'm kind of off on a tangent, but I just want you to see how things vibrate, how things can look when they're vibrating in one dimension. What happens if you look at this 2D harmonics, right? And two-dimensional harmonics. Let's see. I probably can just get some pictures. I want to see pictures. Some pretty pictures. I want pretty pictures. Oh, I wonder if Wolfram can show me. harmonics of a circular plate. I'm just curious. I just put it into Wolf. Ah, dang it! It gave me an equation. Sorry. Let's see. Harmonic. Let me put harmonics of a circular plate. Oh, that's pretty good. That's pretty good. Hold on. Okay, so actually, I could show you guys what I'm searching for. So these are kind of, you guys have never seen these before, maybe. So a circular membrane, that's the right word. Okay. Oh, these are great. That's exactly what I was looking for. Okay, so this is actually how a two-dimensional object, a circular object, might start to vibrate. And these are called the harmonics as well. And so this is the simplest one, right? And this would be kind of like your fundamental. And then here's another one. It's kind of cute, right? It vibrates up and down. You got an additional node in the middle, right? And then you've got this one where you've got it vibrating in multiple ways, right? Kind of cute. This is really great. I like this one. This is nice. Okay. So anyways, you're seeing a two-dimensional object. Woo! Look at it go. Oh, these are fun. Oh, I like these. These are wonderful. These are all different ways to vibrate a two-dimensional membrane. Okay, that's fun. These are really great. Okay, let's try it again. Actually, I wonder if they have sphere. Ooh, I like these guys. These guys are nice. Let's see, who do I talk? Where are you guys? Dan Russell. Let's see if Dan Russell has done any more. 3D sphere. I like his visualizations. Okay, unfortunately, I don't think. Let me see. No. Oh wait, SPHE. Oh, scattering from spheres. No. Okay, so let's put. These are actually well-known mathematical equations too. Harmonics of a sphere. Okay, yeah. I like that oscillation thing though. That is so cool to see. Let's see if I could put animation, because that was really neat to see. Spherical harmonics. Can we see animations? They're not animated. That's boring. All right. Well, anyways, I guess I'm gonna, maybe you guys could look for something, see if you can find it. But anyways, if you take a sphere, a three-dimensional object, that looks pretty good too. But yeah, I can't see it moving. I want to see it moving. Maybe if I search YouTube, huh? If I search a video. Ooh, spherical harmonics. Should we try that? That does not look, that's not right. No, that's too funky. Ah, that's cute. All right, but that's not what I want. Okay, I just want simple. Come on. Standing waves in a sphere. There we go. Okay. Oh, these are boring. No, that's not it. Okay, I'm not finding it. Parametric 3D, spherical harmonics. Oh, maybe here. Let's see. So these are actually, okay, hold on a second. This might be okay. These are actually some different functions. Anyways, okay. Yeah, they look remarkably like. Yeah, these are actually equations to describe molecular orbitals inside of an atom. Okay, I'm actually getting off topic. So let me go back to where we're supposed to be. So we talked a little bit about harmonics, and the idea is that the strings are these small little pieces of energy that are vibrating. So the strings are these, they're everywhere, right? So does anybody remember, did they talk anything about, how the strings work? Like what is a string? Is a single string anything? Is a string anything?
I think he went so far as to say it's a bundle of energy.
Okay. Strings are energy. That's good. Did they talk about how to put them together yet?
No, not yet.
Not yet.
Not in the
Okay.
first episode.
All right. So actually, let's go ahead and does anybody know the answer to that question? Do you know how you can put together strings? This is what you're going to cover in the next couple of episodes, but I thought maybe they would allude to at least part of it. Okay, so here's something you should know. Actually, let me go back to my paper. It turns out that the strings are not necessarily tied down, right? Actually, that's kind of an important part. In fact, I shouldn't give it away, but I'm going to give it a little bit away. Okay, so there is the concept that space-time may be warped and have some some shape and structure, right? So there may be like this is supposed to be like a little piece of space-time, and I can't see the grid, but the idea is there's a grid of space-time, and I saw a really cool animation of that. But anyways, so there's some grid of space-time that still looks pretty rectangular. It's supposed to be distorted. It could be that the strings are somehow attached to space-time. Okay, and there's a little uncertainty here. How do they get attached, right? Well, it turns out they can be attached. They can be attached, right, at one end, right, at both ends, or not at all. Okay, so it can be very well connected to the state, the space-time, or not, right? And actually, then the question is, what does it mean to be not at all, right? Well, so then you have the string. Let's just take this not at all case, right? What are the possibilities with that? Well, maybe the string just wiggles off on its own, right? It's not attached to anything. It just kind of wiggle. And things can wiggle and have vibration. It's a little bit different maybe, but it turns out if you take I said my harmonics of the string. I should have talked about harmonics of other things too. If you take a piece of metal, a metal pole, and if you bang on it, you'll see that it starts vibrating. And one of the easiest things to do is to hold it in the middle, right? You hold it in the middle of the bar. And then what happens is that the bar can start moving, and it actually moves a little bit in a funny way, right? It'll actually make a U. Actually, how do I draw this? Okay, it distorts itself up, and it distorts itself down like this. It's wiggling up and down if you're holding it in the middle. It wiggles, and the wiggling has a particular vibration and a sound, right? So these strings could be like that bar of metal, maybe. They could wiggle on their own. But there's really another idea, and the other idea is that they are attached to each other and form rings, right? So they do not have to be attached to the space-time. They could be just wiggling like this, or attached to themselves. And in string theory, you're going to hear some ideas, but it might be that a single string is a particle. It may be that a single string is a particle, but it may also be that the particles are not single strings, and in fact made up of several strings put together. So the idea is that you take this simple tiny thing, it doesn't have much to it, it's just a little tiny thing, and then you start connecting it, and you can, I don't know how it connects, maybe only on the ends, right? But you could imagine having a network of these, right? And it could be triangular or it could be rectangular. I mean, there's really no limits. I don't know what they are, right? There's 4 different strings here. And this thing that you created is not a single string anymore, but it's made up of these tiny little pieces, right? And this composite object, right? Composite object may be a particle, right? Maybe a higher energy particle, right? Because you have more things. But it may be that a higher energy string is how you get that. We don't know, right? I don't know. But there are going to be a number of these things. Here's a question for you. Are strings going to be particles or something else, right? Are strings only particles? Anybody know?
Well, wouldn't they be particles and waves?
Particles and waves, okay. And waves, that sounds good. I like it. Okay, that's great. Are they anything else? So what is string theory? What is what is the goal of string theory? Okay, what is the goal? What are we trying to achieve? Right? What is the goal of string theory?
Maybe to combine gravitational force with the smaller forces.
Okay, sure, that definitely is the case, right? But what does that mean? What do you mean by that? How do you do that? What does that mean? When you say gravity, you're thinking about general relativity, right?
Yeah.
Smaller forces, what do you mean? Go ahead, describe, say them, say them.
Like strong and weak nuclear force and electromagnetic force.
Okay, so the strong and weak nuclear force and the electromagnetic force, all of those are somehow going to be explainable through the string theory. Okay, so what does general relativity give you? You said gravity, but what else does it give you? So I mentioned to you today, I mentioned something important. I don't know if you paid attention. Do gravitational waves need a medium?
Yeah.
What is it? What's the medium?
Dark matter.
No, you're just waving. Ah! Who was paying attention? I wrote it down for you. Come on. Who wrote it down? Huh?
Space-time?
That's right. I wrote that down for you. And I'm trying to give you a little hint there because what does that mean? There's something, right? Space-time is not just an idea. It's something, right? And what makes that something?
I don't know.
Anybody? What makes space-time? Is it a separate thing? Do we have string theory embedded within space-time, or is string theory going to try to explain space-time as well? What is space-time? What is it? What is space-time? Could somebody tell me what space-time is? I don't know if I've ever defined that. Have I? What is space-time? I mean, I think I've mentioned it, but I talked about 4 vectors. I told you about it. No, I don't know. I don't know that much about space-time. What is it? What does it mean? What's space-time?
I see space-time as the realm we're living in where you can move around while just moving forward in time, since we haven't been able to move in any other direction in time yet.
So is it just a mathematical idea, or is it actually something? Does it have structure, and does it have strength? Does it have flexibility? Can you vibrate it?
Yeah.
Yeah.
Like a string, right? Like a fabric, right? Does it vibrate, and can you make waves go through it?
Yeah.
Yes, of course. So now you have to say to yourself, how does that work? What's going on? What is the fabric? So I'm going to use that word just to help you kind of make it more tangible. What is the fabric of space-time made from?
Lots of woven strings.
There you go. Okay.
Oh.
I was waiting for somebody to say that. Okay.
I've been
String
wanting to say it,
theory
but I felt
not
so-
only encompasses the particle matter and the things that you and I are trying to explain, but the fabric of space-time itself is made from the strings. So this is a really interesting idea. So when I drew this picture for you of space-time, what I didn't tell you, but now maybe you can look at it and think about that, is that this grid is exactly made of little strings that are tied together. That's what it is. I didn't really tell you that. I made it space-time and then I attached a string, but actually space-time is made of strings as well. Not a single one. Actually, they're going to use a word. I don't know if they've used the word yet, but does anybody know what a grid of strings is called? It has a name that's really quite beautiful that you want, or I don't know if it's beautiful, but it's useful. What is a string grid? And it doesn't have to be a grid like this necessarily, but the word reflects the concept that they're interconnected with each other. And so they have a topology. They have a topology. They have a surface structure. Have you heard that word? I don't know if I've used that word, topology. It's a mathematical term. What is topology?
I don't know if I've heard you use it before.
It means the shape and structure, right? It's the shape and structure. It has curvature. Oh, we've talked about curvature, haven't we? We've talked about, have we talked about curvature very much? I don't know. I feel like maybe I left something out on that, but we talked about black holes and white holes, right? They have the opposite topology. They have an opposite curvature. Yeah, I don't know if I talked about that very much. We did talk about negative energy density. Yes, I think we did talk about that, but maybe I forgot to tell you that that reflects an opposite topology. So you can have positive and negative curvature. Positive curvature is something you and I are familiar with. Positive curvature is associated with positive energy. Comes from positive energy. Negative curvature, sorry, there's just an A, is negative energy. Okay, so anyways, topology, space-time. What is the name for a grid of strings that are stuck together to form this topological surface that we might call space-time? And the word that you're gonna be hearing is a mesh. A mesh. A mesh is a cohesive. What is? There's a bigger word. There's a not cohesive. What's the word? Coherent. Coherent. I don't know if coherent's the right word either. All right, whatever. A grid. I don't know. Grid. I'm gonna put grid. A grid of connected strings. So you want to pay attention when you hear that word mesh. That you're talking about a larger object, a much larger composition, composite of strings. And this mesh describes space-time. And then this mesh may also describe more complex particle situations. All right, so what is the goal of string theory? Anybody state that for me? What is the goal of string theory? We've kind of danced around it a little bit, but what is the ultimate goal? We actually, you know what, Leonie kind of told me, but what do you say? Can anybody say it? To unify.
To unify general relativity and quantum mechanics and all the forces of nature.
So why don't we just say, can we just put all the laws of physics, of physics in one income, you know, all, he uses this word, all encompassing, right? Theory of everything, right? He uses that all the time. Actually, it's in the beginning section, right? It's a theory of everything. The theory of space or matter? Space-time? Yep. Matter? Yep. All of that. Everything. The forces, the energy, the matter, the space-time, everything, right? And that's a big goal. And so, you know, you've gotta reach. It's not going to be an easy thing to do. So as of today, how many experiments have been done? How many experiments have tested string theory? Does anybody know the number?
0?
That's correct. None.
Aw.
Okay. So that's not good. That's a bad thing. That's this is a problem, right? This is a big problem, because is it science? If you cannot test it, is that science?
It's philosophy.
It's yeah, I mean, we believe that the path that they're on will lead eventually to predictions. Okay, that's what we believe. Otherwise, people would not have spent their entire lives and careers pursuing this. They believe fervently, right? I mean, if you talk about religious belief, that's one thing. But do you know how much you have to believe in string theory to spend 50 years of your life dedicated to discovering how it works and not know at the end if it really is going to work? But people are so convinced because it's beautiful. It's amazing, right? It has an elegance, it has beauty, it has symmetry, it has things that we consider to be really powerful and important ideas embedded within it. And it may be that they're right, but right now it has not been tested, so that's a problem. Okay, so yeah, okay, so that's it. I have to give you this quiz, and I actually debated. I'm not going to give you a regular quiz like with all these multiple choice questions. Maybe I'll have throw in a couple, but I have some essay type questions to ask you today. And actually, I've been looking over our, you know, what we still have to cover. We're almost done with the book now, though. This is kind of like the big thing at the end, right? Where we try to pull it together. All of these ideas that Hawking has described. Actually, his work really influenced string theory heavily. And so you want to be aware that it's kind of exciting that we read his book and then look at the future of it, right? What comes out of his work, his ideas are some really big ideas in string theory. Okay, let's see, where's my second question? I forgot, where is it? I have another question for you. I was just going to give you, okay. All right, oh, this is actually in your first episode. Okay, so when they talk about Newton, right? It's actually kind of funny. I'm giving it away, but you're watching the video, so you guys are interacting with me. He talks about Isaac Newton, and I think it's kind of a fun thing to think about. What was the embarrassing truth behind Newton's theory of gravitation?
Oh, I loved that.
Isn't
He didn't
that
know
cute?
how it worked.
He had no idea. So actually that leads us to an important part of science that you should be aware of. There are many things that we can observe, and we could try to come up with, we could recognize a pattern, and the pattern that we see is real, right? There's a pattern there. Actually, biological sciences especially, in the beginning, you didn't know the cause and effect. We still don't know, right? I mean, here we have this incredibly powerful virus that is, you know, killing more people than ever before. It's the most horrible virus that we've had in 100 years. And we don't understand exactly how it works, because we don't understand at a fundamental level how our bodies work, right? We have a pretty good idea, but there's still so many questions that need to be answered. I mean, we know about DNA, right? Or does everybody know about DNA? Is DNA real? Actually, I know it's real. DNA is real, but it turns out, I don't know if you guys know this, but an individual person can have more than one set of DNA in their body. Did you know that?
Yeah, from genetic mutation within different cells, right?
Well, I guess so. I guess that's how it works. But I mean, really, it's like, I thought the DNA was meant to be the unifying, kind of blueprint for our entire body. And that's my misunderstanding. I didn't quite understand that. Maybe it's genetic alteration. That could be what it is. Maybe that's all it is. But I think that there's even more variety than that. And it's just, we are more dynamic than we realize. And the dynamic time scale is so short for us that we can't really perceive it very well. But things, the actions inside yourself, the fact that you can think, on a time scale of less than 1 second, means that there are events going on within your body that power that, right? So how is my brain able to function? And here I am, I didn't write the script. I didn't write the words that I'm saying right now. I'm just experiencing this class, and I want to share my ideas with you. And just like that, the words come out, right? How does that happen? How is it possible? How are my memories being created right now in exactly the moment that I'm living them? How's that possible? And that's, anyways, I'm off on a tangent, aren't I? So the second question I want to ask you is, I already did. I asked it, of course, Newton, right? So I know what I wanted to say. I got off on a tangent. I wanted to tell you about Newton, right? So for Newton, he didn't really know what he was doing, but he did a pretty good job. Newton's law of gravitation, pretty powerful and useful. Gravitation, pretty important law, and we were able to use that law to talk about even understand the event horizon of a black hole, right, using very simple formulation of Newton's law of gravitation. But he did not know why it was, did not know how or why it worked. So what do you call a scientific theory that is based on good observations, that shows a pattern, right, but does not understand, right? There's no underlying identification of why it works, right? And this is really, it's known as empirical. Okay, empirical. So based on observations. Okay. So an empirical formula, an empirical law is based on data that you collect, right? It has hard data, but it's not based on not on an underlying theory of how the system works. So general relativity is better in some sense, because why? What is general relativity? General relativity says, actually, okay. So general relativity is Einstein's description of space-time, right? Space-time, but there's two things, right? It describes the matter energy and how it affects curvature, right? It curbs space-time as a result. And then from all of that curvature and matter space-time, we get we get the appearance of gravity, right? But it's a manifestation of this larger understanding of the curvature of space-time. So matter energy curvature of space-time causes the feeling of gravity that you and I are used to, or the attraction that we see in the universe, right? And then it also explains other things that are much more than that, right? It explains It also explains gravitational waves, right, and how they propagate. And one of the neatest things that I'm so excited, I wish he was around to see it, right? But he predicted that gravitational waves should exist. He never found out that they really did exist, but we now are routinely seeing them, right? They're routinely being perceived. And I actually, I'm thinking of something else I want to do. So I'm gonna give you a kind of a smaller assignment. I already gave you the assignment to watch the rest of the videos. But I want you to actually see the scientific papers as well. And I'm thinking of one in particular. I want to show you the first gravitational wave paper. So maybe what I'll do, well, I can make it for next week too. But it's just such a profound thing. Have you guys, did I ever show you the chirp? You guys know about the chirp? Gravitational wave chirp? Have you guys seen that? Anybody seen that? Know what I'm talking about? The merger of the black holes? Okay. No. Hello? Hello, Lonnie? Did you
Sounds
see it?
familiar.
You haven't seen it though?
I don't think I have, or at least not for quite a while.
Okay, so let's take a quick look then, and then when you see the when you actually look at the first paper, it's kind of a fun thing to understand, and we won't do any calculations related to it. It's mainly just to look at it and just be aware. This is a historical moment when we first were able to feel the vibration of space-time and measure the event that caused it. So let's just go to here and go to LIGO, gravitational wave chirp. Okay, so the sound of two black holes colliding. Oh, let's do this one. All right. Well, actually, this is the original. Oh, I turned off the sound. Hold on. Here, let's start it again. Sorry. So they actually scaled them up to a sound frequency that we could hear. But that chirp that you see is the two black holes are orbiting each other and then gradually getting closer together. So they speed up as they get closer together, and then they merge, right? So that actually, you know, there's a black hole merger animation. I could just show you that too. Let's just see that. Black hole merger. Because that actually shows you the gravitational waves. Oh, this one is right here. This is fine. Georgia Tech. Ooh, that's pretty cool too. Ooh, that's pretty cool. I think this is pretty good. I like this one. Okay, so the two black holes. These ones are showing you two different sizes, but you notice that they're getting closer together. And the process of them spiraling around, their great mass is actually creating disturbances in space-time. And there they've merged. And actually at the end, there's kind of an increase in the size of the waves, right? Actually, if you go back and look at that again, and there's a big like burst of activity. The waves get larger and larger, the disturbance is getting larger and larger, and then boom, right? And there you have this big wave front moving away, and that's the chirp of the final merger. And then it's kind of quiet, right? Things are quiet. So at that point, they would stop making so much noise, right? Or vibrating space-time. But that's kind of a neat thing. All right, so we will we'll expect you guys to watch the rest of the videos. There are some really wonderful pieces left. Please, everybody, please watch them. And I have a very short quiz for you today. And actually, we've already discussed the two questions I'm going to ask you. Maybe I'll throw in one more idea, multiple choice question. But then watch the videos for next time. And then next week, I will give you an assignment to look at the first LIGO paper from the gravitational wave merger of two black holes. And that was 2015, September 15th, 2015, 5 years ago, not even 5 years, 4.5 years ago. And it really is a huge revolutionary moment, right, where things are going to change forever. So we now have gravitational wave observatories capable of feeling the vibration of space-time, and it's just the first one that's operating, right? The first set of observatories that are operating. But we have plans, there are plans to build bigger ones and more sensitive ones in space, and that will lead to even more discoveries. In fact, maybe even more discoveries than have ever been made by telescopes, right? Telescopes which see light, because these ones can see through everything. The gravitational waves go through everything. Okay, so that's it for today. Thank you guys for being here, and look for that participation quiz. Please watch the rest of the videos. And also, if you have not been doing your outside activities, I know I haven't graded them, but I will grade them, and they are part of your grade. So please don't neglect them. There are lots of ways to do this. Actually, we do have a guest speaker, a real person who's coming just for us a week from Friday. That is Friday the 24th at 1 p.m. We'll have a live presentation. This is Jared. Some of you guys know Jared. He's a graduate student at UCSB studying supernovae and large mass stars as they supernovae. And so he'll talk about his research and some other topics. And you can use that as your outside activity if you don't have one. And again, you have other opportunities with the recorded videos. All right, well, thank you guys very much. Have a wonderful day. We'll see you next Monday. Bye.
Thank you, you too. Bye.
Bye.
Thank you.
Thank you. Have a good
Thanks,
day.
Sean. I'll see you on Friday.
I'll see you Friday. Yeah, sounds good. Bye.